Okay, so we're looking at Chapter 7, Work in Energy. Basically, you're going to focus primarily on mechanical energy, and this is any energy that is associated with motion. Maybe kinetic energy, maybe potential energy. It could even be work, which is mechanical energy added to a system. But there are many forms of energy, and really, when we look at different things in physics, different processes in physics, things that are interesting, processes that are interesting, take place when there's a transformation from one type of energy to another type of energy, be it chemical to thermal to electromagnetic, nuclear to mechanical, whatever. When energy is transformed from one type to another, that's when we start observing interesting phenomena. Now, one of the most important laws associated with energy is conservation of energy law. And we have to be careful. The energy has to come from someplace and has to go someplace. You can't create energy out of nothing. You can't destroy energy into nothing. Okay, so again, in this chapter, we're going to focus on two forms of mechanical energy. And mechanical energy, again, is energy that we associate with motion. The first type is what we call work. Work is that mechanical energy that we add or take away from a system using some sort of force. So if we want to increase the mechanical energy of a system, we will add work. If we want to decrease the mechanical energy of a system, we will remove it by doing negative work. The other type of energy that we'll talk about in this chapter is kinetic energy. Kinetic energy is the actual energy associated with motion. Kinetic energy is related to the mass of the object, but it's also related to the square of the object's speed. The last type of mechanical energy, we will touch in some examples, not in very much detail, but is potential energy. This is stored mechanical energy that we can use to eventually become either kinetic energy, okay, or be used to do work in some other way. So again, energy considerations. Energy can be transformed from one type or one form to another, okay? Again, the total energy in any closed system is going to be constant. And that means that in any system, you can't change the total energy if there's no energy coming in or going out. In fact, we can look at the universe as a closed system. No energy can come into it or out of it to the best that we know. The conservation of energy and following where the energy goes is essential to other studies such as chemistry, biology, geometry, and astronomy. We can use conservation of energy in addition to Newton's laws to basically understand just about any classical system. The other added bonus with energy is because it's a scalar, we don't have to analyze things to the level of detail that sometimes we need to do with forces. So sometimes we can even use it in place of Newton's laws of motion to try to come up with an outcome, to try to predict how a particular system is going to behave. Our SI units of energy are the joule. The joule is named after James Prescott Joule. And James Prescott Joule was the scientist who demonstrated that heat was a form of energy. He did this by converting potential energy from weights into kinetic energy in a pulley system, which eventually was then doing work on a calorimeter. And as work was done on the water in the calorimeter, he would watch the temperature go up proportional to the amount of potential energy that he used up. So again, this was one of the first conservation of energy demonstrations. He was able to demonstrate that by putting mechanical energy in, that mechanical energy could be lost as heat, and that therefore heat must be a form of energy. So we've named the joule after him, again, 1 joule. is roughly equal to the amount of work done when we push an object with 1 Newton of force for a distance of 1 meter. Notice that we have both a force here. The force is what is putting the energy in, and we have a distance. If we don't have any movement, we're not adding mechanical energy to this particular system. We can further break down the Newton to a kilogram meter per second squared. If we multiply that by meters, the joule becomes 1 kilogram meter squared per second squared. Now, here's some examples of energy. And we're just going to look at orders of magnitude here. It's sort of interesting to compare different things. Really, if we're thinking about sort of the lowest energy that we can talk about, 3.0 times 10 to the minus 31 joules is the average kinetic energy of a molecule cooled down to the lowest temperature that we were capable of doing in 2003. And I don't think we've gone much lower than that. But that's the lowest energy that we've been able to obtain in a single particle. The electron volt is an important unit in particle physics. It represents the amount of energy an electron will get by accelerating it in a 1 volt field. What else is here? Oh, photons in the visible part of the spectrum have a few EVs, or a little bit more than 10 to the minus 19 joules of energy. And here we have 1,000,000 electron volts, so the mega electron volts down here. And finally, deuterium-tritium fusion releases 2.26 times 10 to the minus 12 joules for every fusion event. Deuterium-tritium fusion is what we hope to use in fusion reactors. Oh boy, the fission of a uranium-235 atom. 3.2 times 10 to the minus 11 joules. We think of nuclear power as liberating a tremendous amount of energy. But when we look at it per particle, there's actually not a whole lot of energy there. By Einstein's theory of relativity, we can say that E equals mc squared. If we convert the mass of a proton or a neutron into just pure energy, that energy equivalent is 1.5 times 10 to the minus 10 joules. More exotic particles like the W and Z boson, which were discovered fairly recently, have about 10 to the minus 8 joules of energy. We don't oftentimes use this form of energy because, this unit of energy because it's in the CGS system. But in the CGS system, 1 erg is equal to 10 to the minus 7 joules. And if we're thinking about the kinetic energy of a flying mosquito, it has, well, perhaps about 1 erg and a half of kinetic energy, about 1.6 times 10 to the minus 7 joules. Oh, now we're getting some more. 1 second of moonlight falling on your face comprises of about 3.0 times 10 to the 5 joules of energy. And this, of course, is during a full moon. Crickets chirp, 9 times 10 to the minus 4 joules. American half dollar following 1 meter, about 1/10 of a joule of energy. Okay, now we're getting up to the joule itself. Another way of expressing the joule besides the Newton meter is the watt second. We'll be talking about kilowatt hours a little bit. The kinetic energy produced by a small apple falling 1 meter to Earth, as in Newton's demonstration of falling objects in the moon, the universal law of gravitation. Oh, a quiet person produces about 1 joule of heat every second. The energy required to heat 1 gram of dry, cool air by 1 degree Celsius is also 1 joule. Now, later on, we'll talk about metric calories, what we oftentimes call the small calorie, or the thermochemical calorie. That's 4.1868 joules, or the amount of energy needed to take 1 gram of water and raise it by 1 degree Celsius. If we look at the most energetic cosmic ray ever, it had roughly about 50 joules of energy. An average person swings a baseball bat with about 80 joules of energy. 1 horsepower is roughly about 750 joules of energy, and a lethal dose of X-rays is about 900 joules of energy. But of course, that's ionizing radiation, so that is energy in the particles that are breaking the bonds of the proteins in your body. British thermal unit. We see this pop up quite a bit, and we'll talk about this in reference to air conditioners and heaters. The British thermal unit is roughly 1 kilojoule, okay, about 1,000 joules. And that's also roughly about the energy, or the total solar energy that we receive from the sun over every square meter on the surface. This is actually a little bit less after it goes through the atmosphere. Okay, food calories. Food calories are 1,000 times bigger than the small calorie. So that's how much energy is contained in 1 food calorie, 4,186 joules. 1 gram of sugar has 1.7 times 10 to the 4 joules of energy, or roughly 17,000 joules. Here's the interesting thing. When we eat food, we think of sugar as being very fattening, having a lot of energy in it. But in fact, when we eat fat, 1 gram of fat has more than twice the energy of 1 gram of sugar. So if you're talking about energy bars and whatnot, generally you can get more energy out of eating an equivalent amount of fat compared to carbohydrate. Of course, the one thing that you would never want to consume is 1 gram of gasoline. Contains even more energy, about 50,000 joules. An automobile on a highway, if we take a look at its kinetic energy, has anywhere from 200,000 to about 900,000 joules. Here's what's amazing. I love this. A Mars bar has about 1 million joules of energy, and that's roughly 250 food calories, just if you want the conversion there. Kilowatt hour, this is an important unit of energy. The kilowatt hour is 3.6 million joules, or 3.6 megajoules. And to not exceed, but not eat too little food, the amount of food energy that you should take in is roughly 8.4 million joules. Okay, you can convert that to food calories if you want. Roughly about 2,000 food calories. If you perform 1 day's worth of heavy labor, you'll expend about 10 million joules, or 10 megajoules of energy. And a 55-ton aircraft traveling at about, traveling well over 100 miles per hour has 100 million joules of energy. Okay, now we're getting to more. Want to melt a ton of steel? It will take you 1.2 billion joules of energy. A lightning bolt, that means an average lightning bolt has more energy than it takes to melt steel, 1.5 billion joules. Give you an idea of how hard your heart works. Your heart will expend 2.5 billion joules of energy over your entire lifetime if you get to live to 80 years old. And 1 barrel of oil, and that's crude oil, has 6.12 billion joules of energy. All right. Airbus A380, the largest of the aircraft, when in flight, has about 23 billion joules of kinetic energy. The average automobile will consume 72 billion joules of energy. Atlas rocket, almost 1 trillion joules of energy taking off. And the International Space Station, which took many rocket flights to put up in orbit, its orbital kinetic energy is 8.2 trillion joules. Okay. Now we're getting to really big things. Average thunderstorm releases 36 trillion joules of energy. I think that's sort of a repeat. The first atomic bomb dropped in World War II released 63 trillion joules of energy. The second, 88 trillion joules of energy. And if you took 1 gram of matter and converted it all into energy, that would account for 90 trillion joules. A megaton of TNT, oftentimes we use this as a measurement to rate explosiveness of nuclear weapons. It has 4.2 petajoules of energy. Oh, average hurricane will expend 0.6 petajoules every second. That's how destructive they are. You ever travel to Arizona, see the Barringer meteor crater? Whatever created that gave off about 10 petajoules of energy. And 1 kilogram of antimatter annihilated with a, well, got to be careful here because we need basically 0.5 kilogram of matter and antimatter to annihilate, roughly 90 petajoules of energy. So really getting to large amounts here. So the largest earthquakes ever, 10 to the 17 joules. The largest bomb ever built, the Tsar bomb, built by the Soviet Union, which was 50 megatons, released 2.1 times 10 to the 17 joules. Krakatoa, 8.4 times 10 to the 18 joules. And again, just going down here, Chilean earthquake, which was 8.8, one of the most powerful earthquakes ever. 6.66 times 10 to the 19 joules. So we're looking here, the yearly energy consumption of the United States. We can measure in exajoules, about 14 exajoules. Daily energy released by an average hurricane, 52 exajoules. And the yearly energy generation of the world, 62 exajoules. All right, let's jump ahead a little bit. Just we're getting a little bit tedious here. How much energy strikes the Earth every day? 10 to the 22 joules of energy. This we use a new metric prefix, the zetajoule. The zetajoule, 15 zetajoules of energy strike the face of the Earth just from solar energy. And that's why solar energy is seen as being such a great potential source of energy. And over the entire year, we can measure that energy in yada joules. These are really interesting metric prefixes. So 5.5 yada joules strike the Earth every year. All right. Total energy output of the sun each day, 10 to the 31 joules, well, 3.3 times 10 to the 31. The kinetic energy, here's something that's interesting. People always ask, well, how much energy would you need to break the Earth free from its orbit? You would need 2.24 times 10 to the 32 joules. I'm sorry. Let's go back on that. To break the Earth from its orbit, you would need 2.7 times 10 to the 33 joules. If you did this by slamming something into it, before you'd actually break it free of its orbit, you'd basically blow it apart. The Earth's gravitational binding energy is less than our potential energy. So, all these science fiction movies where they scheme of ways of knocking the Earth out of the orbit, you destroy it before that would happen. The sun puts out 10 to the 34 joules every year. And the most powerful explosions in the universe, a supernova, 10 to the 44, a hypernova, which is actually the type of supernova that can sometimes be created when a black hole forms at the center of a very massive star, 10 to the 46, can also be accompanied by a gamma ray burst, 10 to the 47, equals mc squared, all the energy in our galaxy, 10 to the 58. If we include the dark matter and dark energy, it goes up to 10 to the 59. And all the energy in the observable universe, somewhere around 10 to the 69 joules or 10 to the 70 joules. But that's a little fun trip looking at all the different scales of energy. Of course, most of what we'll be looking at are just practical examples of energy. And in particular, we concentrate here on mechanical energy. SI units, once again, the joule, 1 Newton meter, or 1 kilogram meter squared per second squared. We did talk about the calorie. We said that the calorie was 4.186 joules. That represents the amount of energy to take 1 cubic centimeter of water, or 1 milliliter of water, or alternatively 1 gram of water, and raise that by 1 degree Celsius. And again, here's a conversion between the two. There's roughly a factor of 4.2 between them. More precisely, it's 4.186 joules per calorie. And you can multiply 4.2 to go from calories to joules, or divide by 4.2 to go from joules to calories. Food calories, as we said, are different from regular metric thermal calories. Food calories are technically kilocalories, which means that they are thousands of metric calories. So when you look at the nutritional fact on a serving label, what you're actually seeing there are not 250 metric calories, but 250,000 metric calories of food energy. Again, many times we look at food calories as being negative because our body will store the excess chemical energy in our fat cells. However, it's important to understand that if we eat the right amount of energy or the right amount of food, this energy is very critical for keeping us alive, for providing the energy necessary to make our heart pump blood, to allow our diaphragm to move our lungs, and for our central nervous system to work. All this uses up chemical energy, and most of this chemical energy is turned into heat. Our electric bills, when we receive an electric bill, they're typically shown to us in how many kilowatt hours we've consumed. Up here, we can see a chart showing kilowatt hour usage per month, and this is shown in the hundreds of kilowatt hours. And when we look at a bill, we are charged by the power company by how much energy we take off the grid, and therefore how much they have to replace from what we take off the grid. And they send us a bill according to that. They charge us by how many kilowatt hours we're using, and they'll actually sometimes come up with a variable rate based on the number of kilowatt hours we use in a certain time period, and if you have time metering, the time that it's used. So the kilowatt hour is roughly it is 3.6 million joules of energy, or 3.6 megajoules if you want to use that metric prefix. Now, electric vehicles use lithium-ion batteries. Instead of storing the energy in gasoline, the energy is stored coming off the grid. This energy is loaded into the vehicle by some charging cable. And this takes this electric energy and it converts it into chemical energy within these lithium-ion batteries as the lithium ions migrate from one side of the battery to the other. Now, when you purchase one of these cars, they'll tell you how much energy it actually stores in kilowatt hours. For instance, the Chevy Bolt will store 66 kilowatt hours, whereas the Tesla Model 3, in one of the recent incarnations, could store, depending on how much you wanted to spend, 54, 62, or even 75 for the long-range version. Now, this sounds like a tremendous amount of energy. If we look at this, however, and compare it to the chemical energy, which is in a gallon of gasoline, a gallon of gasoline has 127 megajoules per gallon. So again, converting the 66 kilowatt hours into megajoules, we can do that because we know there's 3.6 megajoules per kilowatt hour. We get an equivalent of 240 megajoules for the Bolt, and for the long-range Tesla 3, 270 megajoules. Now again, doing comparison, 127, you double that and you're up to around 230. I'm sorry, yeah, I can do my math. You're around 250, 260. So if you convert the chemical energy from the gasoline, you only need about 2 gallons for either vehicle to go their full range. Both vehicles can go well over 250 miles. So while electric vehicles can be quite expensive, energy-wise, they're very energy efficient when we compare it to a typical car. Doing the equivalent, miles per gallon, both of these far exceed 100 miles per gallon, whereas for the equivalent energy, whereas the typical even economy car would be at best in the 30s or 40s. British thermal units. This is another energy unit. Both the calorie and the kilowatt hour were actually metric units of energy. These are, as their name implies, a British unit or a US customary unit. We still use it today, and oftentimes we'll use it in reference to how much thermal energy a furnace can produce. Of course, it's producing it from the chemical energy stored within the fuel, or how much thermal energy an air conditioning unit can move. So one British thermal unit is roughly 1 kilojoule, or more precisely, it's 1.055 kilojoules. And if you're buying an air conditioner, you can look up a sizing chart to compare what the size of your home is to whatever needs you have for an air conditioner. So for instance, let's say you just want to, cool down a small room. Maybe it's a 10 by 10 room, not very big at all. You wouldn't need a very large air conditioner at all. If you wanted to cool down your entire house, however, okay, even a smaller house or a smaller apartment would use about 25,000 BTUs per hour to keep it cool. Furnaces, it's pretty much the same thing. However, you've got to be concerned about where exactly you live. Depending on where you live, your heating needs will be less. Obviously, if you live in the south, in this first zone, you don't need very much heat at all. About 30 to 35 BTUs per hour per square foot is sufficient to heat a home down there. In New Jersey, you would need to be either 40 to 45, or if you're in the northern part, 45 to 50 BTUs per square feet. Okay? So a 1,000 square foot apartment would obviously require a furnace that could produce 40,000 to about 50,000 BTUs of energy. Whereas if you live up where I live, well, you need a little bit more than that per square feet.